Last time in this class, we looked at shear stress distributions, how they varied, and all that fun stuff. We talked about how they are not uniform across a cross section. Same way that if I looked at, say, bending stress, that's not uniformly distributed across a cross section. It's kind of like I said, it's an my over y over I relationship, where m is your bending moment at a section, I is the second moment of area at a cross section, and y is kind of your distance from the neutral axis. So this little beam here, you can say if this is my neutral axis, then my normal stress distribution, this is in bending, something like this, where it's a maximum at the top and at the bottom, and it's at 0 at the neutral axis. So when we did this for shear stress, we said, well, here's a bunch of math, and it comes out with an equation that looks something like that, where V is your shear force, I, just as in bending, is your second moment of area for the section, T is the width of the section, kind of the into the page distance, and Q is this first moment of area that we take with regards to the stress cube that we're looking at. So if you remember, this is my a beam, and say that it's in bending, so there's some shear force acting on it. And I looked at the cross section in here that I've cut. So here's my section, there's my neutral axis, and say I'm looking at stress at some distance y from the neutral axis. Well, just like we did last week, we said, well, there's a stress cube there, and Q is the first moment of area of that stress cube, or kind of how much area is here multiplied by the distance of the centroid of that area from the neutral axis. So we came up with some expression for a y bar, and Q equal y bar times the area of the stress cube. For a rectangle, this worked out to be a quadratic relationship. Really, for anything, it will end up being a quadratic relationship, but we found it for a rectangle. So for a rectangle, Q equals the thickness, be like that width there, over 2 times c squared minus y squared, where c is kind of like your half height, or if this is h, c equals h over 2. All right, so from this, we know that we look at our shear stress equation and say, well, the second moment of area for a section doesn't change. The width of a section doesn't change. The shear force acting on a section does not change. This is all for a section, remember. The only thing that changes in this scenario is where we want to compute stress at. So where along this section we want to compute it, where the value of y is going to change as we say, okay, I want stress here, or here, or here, or here. So if we wanted to, say, plot variations in shear stress across a section, then we could say, okay, we're going to vary the value of y. I'll draw a little plot here where we say, okay, y is changing along like my vertical axis here, and plot shear stress is just going to the right, and I'd end up having a plot that looks something like this, because in this expression, t is constant, c is constant, y is the only thing that's changing, and it's changing according to its square. So I'm going to get, so my shear stress, since if I substitute in for a Q there, the only thing that's changing is a y squared. So if I rewrite it down here, my shear stress changes quadratically. You can see that my shear stress changes quadratically across this section, going from 0 at the top to 0 at the bottom, but reaching a maximum right along the neutral axis at y equals 0. We talked about that a bit last time. So this is cool, but the point here is that we now have to, just like in bending stress, where you have to care about where the normal stress created by bending is at a maximum. Now we have to care about where shear stress is at a maximum. And we don't just have to care about the value of shear stress, we have to care about how it combines with the normal stress acting on a given point. For example, if this guy is in bending, that means that I also have some, or actually let's do something easier. Say I'm just pulling on it, so I have some uniform normal stress distribution here. So I'm not really adding them together because this is a normal stress, not a shear stress. They don't combine, but I'm trying to say there's more than one stress acting on a given point. If I looked at this point here and I said, okay, will it break there? I have to see how these two stresses are going to make this thing fail. And how we have done that is by using Mohr's circle. Because remember our failure criterion, and the failure criterion that works for a lot of materials, which are called namely ductile materials, which include like steel, aluminum, stuff like that, has been that material will fail when a maximum stress, so we're talking like yields, which is called the yield stress of the material, the ultimate strength of the material, the tensile strength of the material, whatever kind of criterion you're going by. Usually we pick yield because that's when the material plastically deforms, permanently deforms, if you will. So the material will fail when whatever maximum stress criteria that we pick is met by is met through shear stress. So ductile materials usually fail in shear. So if the maximum shear stress that's being experienced by a stress cube in the object that we're analyzing meets whatever maximum stress we've picked, then the material has failed. And we've said through Mohr's circle that which calls that even if something's in pure tension, we can draw this circle, which is really just stress transformations. It's turning that stress cube around, right? Just changes the angle that the thing's going to fail at. And even if something's in pure tension, so that dot there is kind of our applied normal stress. There's what's called some rotation of that stress cube is going to experience a shear stress. So we need to figure out not just what our shear stress is in order to find this failure criteria. I mean, we don't just have to like throw things through this equation and say, hey, am I at this failure criteria? We have to say, okay, are the all the stresses going at this material, normal and shear, the ones that I can compute anyhow, are they going to combine into some greater maximum shear stress that's going to make this thing fail sooner than I think, given the stresses on the material that I can compute? So let's have a look at this. We're just going to do an example of today, looking at 3-point bending. So, pretty simple problem. We've done it before. Have 2 pin supports and a load dead center. So this guy's some L/2 from one side. Whole distance is L. Excuse me. This guy is some load P. It's some supports we know by inspection. We did our summation of moments, summation of forces here. Sorry, there you go. That FL and FR will be exactly the same because they're equally spaced from P, and they equal 1/2 of that applied load. Similarly, we can back up and say, well, if I drew some shear and bending moment diagrams for this, I could figure out what these loads were. So if I look at section here, there's FL there, there's my shear force, there's my bending moment. Haven't gotten to P yet. There's some distance X from the left. You can say, well, V obviously equals FL, and MB, there's only one thing here that makes a moment around this section besides MB, and that's FL. So MB must equal FL times X. Similarly, if I go to the other side of P, so that's where my other section would need to be. There's P, there's FL. For completeness, there's distance there. I'm still measuring X from my far left side so that I'm consistent. Well, I can say that V equals FL minus P, or negative 1/2 P, or negative FL if I want to expand that guy out. Similarly, MB, if some positive directions here. Okay, if it started out with MB equals FL times X, I'm now looking at had P generating an opposite moment to that, so minus P, and it's only generating moment at this much of a moment arm, so I might say like X minus L/2 from the section would be its moment arm. Or if I wanted to simplify this a bit, know that FL is 1/2 P, so this would be like 1/2 PX minus PX plus PL/2, or negative PX/2 plus PL/2, or P/2 times L minus X, if you wanted to condense that puppy up. At any rate, all this to say something that we've seen several times before. You get your shear and bending moment diagrams. So there's X, there's V, and it ends up looking something like this, where this is not to scale, right? It's FL, this is negative FL, or negative P/2. This distance here is L/2, and this is L/2. Similarly, I can draw my bending moment diagram. And I know that it's going to go up linearly and then back down to 0. That's L/2 in the center there. Maximum will be in the center, and I can tell you exactly what that is because I know that what MB equals FLX from 0 to L/2, right? So at a maximum, MB max, if you will, equals FLL/2, or PL/4 if you want to vary through in terms of your applied load. Cool. So we got our shear and bending moment diagrams. Now, we're usually interested in like maximums, right? So we went for, say, like maximum bending stress. We said, okay, middle is where maximum bending stress occurs. Whatever, we can find bending stress. So now we're going to say, okay, we're at the middle. This section, we draw a section at L/2. So section taken at L/2, it's a rectangle, so there's my neutral axis. It has some thickness T, some overall height H, some half height C, just so that we have some convenient nomenclature here, and Y is going in that direction. Okay, so if I said, find me the stress up there, well, by inspection, I know that there's some normal stress there because there's some bending. So My/I is my ticket to ride. I can say, well, MB is what? PL/4. Y is H/2. And I, because I'm bending around this axis here, would be like 1/12 TH cubed. And bam, I have an expression for the normal stress that is maximized there, or if I just put a negative sign in front of it there. And at either of those points, tau xy by inspection would be 0, because, well, if I go back to my VQ/IT thing, and that's really V/IT times what? T/2 H/2 squared minus Y squared. Well, Y equals H/2 at this sigma max point, so this all goes to 0. Y equals H/2. So tau xy is 0 at the max, at the max and the min. But let's look, say, here, at some point that's not at the top or the bottom. So if we did that, we should call at some point y away from the center. Well, it's MYO/I, and as far as we can simplify that, it's to say PLY, 1/4 PLY, over 1/12 TH cubed. Or if we wanted to simplify that a little bit, we could at least say it's PLY over what, 1/3 TH cubed, or 3PLY over TH cubed, just so we don't have any fractions. Same token, say, well, tau xy, V/2I times H/4 minus Y squared. And that's kind of what we got. That is called, we got two forms of stresses acting on that same point. So if you wanted to say, okay, what is our maximum stress? We have to construct a Mohr circle out of this. So we know the usual gig here, which call in order to construct a Mohr circle, we need to know a center point and we need to know a radius, right? So we know the center point is just sigma average. And sigma average is what? Sigma x plus sigma y over 2. Well, you only got sigma going in one direction. It's only coming out of the page, if you will. So, well, it just comes down to sigma over or to 2, or 3 halves PLY over TH cubed. That gives us our center point. The fun one, as always, is the radius, because that's the one that kind of determines what the maximum shear is going to be, maximum shear stress is going to be. So, if you remember from before, the radius of this puppy is equal to the square root of sigma x minus sigma y 2 squared plus tau xy squared. Remember, what is it? I suppose this, for completeness' sake, this really should be my z-axis, so that x and y are pointing in the right directions. Anyhow, so I've got this, so I can just substitute in my stress, my two forms of stress. I know that sigma y is 0 because I don't have anything, I don't have a stress going like that. That's 0. I only have stress coming out of the page, or in the x direction that I defined back over here. I only have stress acting in that x direction. So I've got sigma x and there's sigma y. So I can go over to my equation for the radius of Mohr circle here, say, okay, sigma y is 0. Substitute in the expression for sigma x that I had before. So I get something like this. So r equals square root of, let's see, 3 PLY over 2TH cubed squared plus my expression for shear stress, B over 2I H squared over 4 minus Y squared, and all that squared. So at this point you might say, what the crap, man? I thought we were going to like get a Mohr circle out of this, but the value of y can change, right? So you're right. Really, you're going to get it as you might intuit, because shear stresses has a different value, and the bending stress has a different value all the way along the cross section. So too, every point along the cross section is going to have a different maximum shear stress associated with it. So that's what this corresponds to, some maximum shear stress that is generated by the combination of these various other stresses. And you're right, you're going to have a different one for every point along the cross section. So what you could do is take this, plot it, and see where that's going to be maximized, because it's probably not going to be at the top, not going to be at the middle, it's going to be at some other point in between. And that's where our true maximum stress is going to be, and that's where this puppy is going to fail first. So that's pretty much how to do this, how to construct Mohr's circle for any given point, especially now that we can account for variations in shear as well as normal stress along the cross section. I expect at least a couple of homework problems in this to get you used to the idea of thinking like this. And that's all I got for today. Thanks for stopping by.